Your mics will be live even though no one's saying anything, so just so you know. Okay. Hello, everybody, and welcome to today's Future in Space Hangout, which is our bi-weekly live discussion of all things related to the future of space travel and astronomy. My name is Tony Darnell, and I'm from deepastronomy.space, and these Hangouts are sponsored in part, and Harley will tell you about this in a little bit, by the American Astronautical Society and the astronautical.org. So I invite you to go to their webpage and check out what they're doing. They are making these Hangouts possible. And today, we've got an amazing one planned for you. I'm very excited about today. Now, no one thinks that getting to Mars is easy. We all know that. We're told about how hard it is. Anytime anyone who's ever working towards getting us there, we get to hear how hard it is. Well, this week we're going to be talking with some people who are really working on some novel ways to get us there. Rocket propulsion is a key component of getting humans to various places around the solar system, and a rocket makes itself move, as most of us know, entirely by expelling its own mass in the opposite direction. It doesn't need anything to push or pull against. But what we don't realize, because we're used to seeing chemical rockets, is that there are several types of rocket propulsion. Now, the most common one is the one we're most familiar with. It's chemical, or it's a conventional rocket, and we've seen these whenever we watch a live stream of a launch, or we happen to find ourselves at Kennedy Space Center and we watch them live. Chemical rockets rely on highly explosive chemical reactions, which are inside enormous tubes, and they force mass downward, and the rocket goes up. But there's other kinds of rockets that are being developed, and we're going to be talking about those today, as well as discuss some of the latest in chemical rocket technology. I mean, there are nuclear thermal rockets, which use nuclear reactions, and there are electric rockets, which use electric power to accelerate propellant out the back. And our guests today are experts in the field of rocket technology. And I'm really excited because we have Dr. Franklin Chang-Diaz. He's a former astronaut and the founder of the Astra Rocket Company, who is working on a new electric rocket design. We're going to show you that today. We also have Joseph Cassady, who I hope will show up later a little bit. He's not quite here yet. He's the executive director of space for Aeroject Rocketdyne, a company whose rocket will be featured in a few days when it launches the Mars InSight probe from Vandenberg Air Force Base on May 5th, something we're all looking forward to. And we also have with us Dr. Dan Herman from the NASA Glenn Research Center, where NASA develops innovative technologies to advance missions in aeronautics and space exploration. So I want to welcome everybody to our Hangout, and I also want to bring up and talk about our, let me introduce our my co-host, Dr. Harley Thronson from the Goddard Space Flight Center. He's in the upper left of my little Brady Bunch thing here. Dr. Dan Herman is in the upper right, and Dr. Franklin Chang-Diaz is down in the lower panel there. So, hi guys, welcome to a Hangout. I'm very excited to have you here. Harley, how you doing?
Doing well. This is going to be I think this is going to be one of our best Hangouts, one of the best of many outstanding Hangouts, because just as you said, whenever we talk about, whenever almost anybody talks about getting to Mars, eventually it comes down to propulsion, a handful of other things as well. But how are we going to get them there? How are we going to get them there safely? How are we going to get them there sooner? How are we going to get them there efficiently, cost effectively? So we have a couple of folks, and again, maybe we'll get Joe Cassady to join us in a little bit, but we have a couple of colleagues who have been working hard for the last several years to answer that question, to give us the tools to answer the questions: how are we going to get there effectively and sooner rather than later?
That's right. And while this is a live broadcast, I want you guys, I've already seen you guys, Galaxia, Andrew Planet, John Suffel, Peter Quinn, all you guys are there on the live chat. Ask us questions, and I'll read them out to you throughout the Hangout. But a vast majority of our viewers are catching this on the replay. So I want to welcome all of you guys for watching this after the fact. Don't hold back, though. Leave comments and questions in the comment section, and I will either answer them myself if I know the answer, or I will forward them to our guests and see if they have time to answer. So you're not out of it, even though you're not here right now this minute. And I have to send out a little thank you to Dan from Canada, who sent this in to me. This is an addition to our Hangout mascot cadre, a Royal Canadian Mounted Police rubber ducky, gravitational wave rubber ducky. I have to come up with a name for him, but right now he's just RCMP Ducky, riding the gravitational waves of the future. So, and we got another one there, Carly. Okay, guys, let me start.
Always professional, always totally professional.
That's always here, folks. So there we go. So, okay. Rockets, getting us, in particular, getting us to Mars. I want to start by introducing Franklin Chang-Diaz. He is the founder and a former astronaut, but a founder of Astra Rocket Company. Hi, Franklin. Can you give us an introduction into what your company is working on? And then I'll go to Dan, too, because he's also working on something very similar.
Right, okay.
As well.
Yeah, okay. So thanks, Tony, and welcome, everybody. It's a pleasure to be here. And so we work on electric rockets. And here, instead of chemistry, as you mentioned, we use electricity to heat the exhaust and make the exhaust as hot as possible. And when we talk about make it as hot as possible, we're now moving into temperatures that are close to the temperature of the sun. And of course, doing that requires for us to do away with materials to form the casing of the rocket, because obviously those temperatures are unsustainable from the perspective of materials. So we use magnetic fields and electric fields to guide and channel and vector these very hot gases, which are no longer called gases, they're called plasmas, and then shoot the material out the back at the proper speed. The higher the speed, the less material you have to shoot, and therefore the less propellant or fuel that you have to carry with you, and therefore the more payload that you have to carry with you. So that is sort of the benefit of the electric rocket. And we are working on a particular type of electric rocket, which is called a Vasimer. And it is a high-power device. It's designed to operate at hundreds of kilowatts and all the way up to megawatts. So we think of it as the sort of the diesel engine of space. You know, if you think of the trucking business of space, we think of it as the diesel engine of space, and that's what our company does.
So here's a schematic that you provided us with on the in a PowerPoint, and this says that it's high power in space electric propulsion. This is pretty important. This will not work if you're sitting on a launch pad on Earth and get you off of that launch pad, right? You need
That's
this is
right.
Once you're in space.
Yeah, and that is true for all electric rockets. They are devices that are suitable only for working inside in space, in the vacuum of space. They do not have yet the thrust sufficient to, lift their own weight of the surface of the Earth. So we will always need the venerable chemical rocket to get us off the surface of the Earth and also to land on the surface of the planet or back on Earth. So the chemical rocket has a very long and distinguished career, and it will continue to be so for the foreseeable future.
It's not going anywhere anytime soon.
It's not going anywhere. It's not going to go away. But now we're talking about rockets that will get us through the interplanetary space.
Okay.
To really go fast, and because that's really what matters. Things are far away, and we want to go there fast.
So let me just read some of these numbers here to make sure I understand them. So here you have P equals 200 kilowatts. That's power?
Power.
Okay.
Power, and that's right. And so the efficiency that you see next to that
70%
is how much of that power that you're putting in as electricity comes out as useful thrust from this rocket.
And what's ISP?
The ISP is a number called the specific impulse, and all that is just the exhaust speed in meters per second, essentially divided by 10. So you can see there that an ISP of 5,000 equates to an exhaust speed of 50,000 meters per second, or 50 kilometers per second. And it is, just so that you know, that is about 10 times higher than the best chemical rocket that we can build. And then next to that, you can see the other portion of the equation, which is the thrust. How much does it really push? And it doesn't push very much.
Is this in newtons?
This is in newtons, and
Okay.
4 newtons is about a pound, roughly. So it's about
pound
what
and
it,
a half.
the weight of this coffee or teacup right here. This is about how much it pushes, not very much. The key here is that it doesn't use very much propellant. So you make up for that by the fact that you don't have to carry so much fuel. And the propellant, we don't call it fuel anymore because there's no chemistry going on. We call it a propellant, and it happens to electric rocket use in our.
Uh-oh, sound has gone out here.
Let me note, maybe we might want to shift to Dan. Let me note that my basic rocketry, the specific impulse, which Franklin was just referring, another way that might be thought of is an efficiency, where very high performance chemical rockets might have an efficiency, as memory serves, somewhere around 400 in the same units. And the system that Franklin is talking about here, we'll hear more from Dan, is about roughly 10 times more efficient, uses its quote unquote fuel 10 times more efficiently, doesn't have as much thrust by a long factor, but 10 times more efficiently than the best chemical rockets do.
Yeah, because that's interesting, because this ISP, this specific impulse of 10, what did you say it was? How much greater was it than chemical rockets?
And just a number to carry away, around 10, it's more than, but it's around 10 times more efficient than the best chemical rockets.
But this thrust is 1.5 pounds. So that's, okay. All right.
But I mean, in space, when people talk thrust to weight, I mean, this is a typical question that people ask, and what is to weight? When you in space, weight is zero because you are in zero gravity or weight. Then you can see that the thrust number. What that really means is that in space, if you push ever so slightly, and you do it for a very time, you go faster. You see, you go faster.
Okay, so right. And that's what you meant at the beginning, where it was going really. This is a faster way once you're in space of getting going, because that impulse is going on for such a long period of time.
Right. A chemical rocket is like a cannon, It's like a cannon, and oftentimes in the astronaut business, we say, we went to the moon on cannonballs. I mean, or people go to space on a cannonball. You don't want to go to Mars on a cannonball because you have to carry another cannon with you to fire when you get there, and then you have to have another cannon to come back, and so on. So the thing is, these are called impulsive maneuvers, meaning explosions, basically. Here we are more gentle, and we are delivering the impulse to the rocket over a longer period of time, after which we end up going faster.
Okay, so let me just I want to bring up some of the points in the schematic, and then I want to show the cool movie that you've got. So this RF power, what these yellow things here? What is that? What?
Those things are antennas. The way we heat or we deliver the electrical energy to the working propellant, to the argon, is by means of electromagnetic waves. Pretty much the same way you heat your cup of coffee in your microwave oven.
Right.
It's the same process, except that we don't use microwaves. We use radio waves, which are bigger waves and special waves that tend to be natural to the conditions of the plasma that we have. So the first antenna, or we don't call them antennas because we don't usually NASA gets confused with antennas. They think it's it's communications. So they get worried about that. So we call them couplers. So we take that first coupler that you're showing there, and that is called a helicon. And that coupler couples electromagnetic energy from the RF generators into the gas, and it turns it into a plasma. It ionizes the gas. And once it is ionized, then the plasma realizes that it is in a magnetic pipe.
Right.
It feels the presence of the magnetic field, and it latches onto it, and it flows downstream onto the second coupler. And that second coupler launches another type of wave, which is called an ion cyclotron wave. And that wave, acts on the ions of the plasma and accelerates them to very high, or heats them to very high temperatures. And then as the magnetic field lines expand, you can see that there's a flaring out of those magnetic field lines. That is a magnetic nozzle. And what that does is it takes the energy stored in the plasma, which is in the form of motion of the particles, we call it temperature, and it organizes it and launches it in a axial direction so that it produces a very high-speed jet, which then gives you the rocket propulsion that you're looking for.
Okay, so
that's all there is to it. Yes.
This is really amazing. It is actually quite simple in concept. It really is.
Simple. That's right.
Here's a picture of the rocket, of a test rocket, I presume, right, in your lab.
This is the VX 200, and this is an engine that's been under testing for a long time now. We've fired it over 10,000 times, but we're getting ready to do a long duration firing with this engine. And there is a little video there.
Let me show this now. Okay, folks, here it is. Here's a test firing of this.
This is what you see here is just the exhaust. So the business end of the rocket, which is kind of hidden behind that wall that you see there, but is shooting plasma to the right. And these probes that are being fed and they move along. They're inserted into the plasma to measure.
Yeah.
We use it to measure the momentum, the thrust of the device, and the performance, the efficiency. Now, these probes don't last very long because the plasma is very hot.
You can't. I don't know if you can see it in the video, folks, but it's going from left to right from our vantage point here. It's just going across the plume this way.
Right. It's about 5 million degrees, that plasma right there. And so those probes have to be replaced pretty often.
Okay, wow, that is really cool. Let me pull this back up. So we have this is something you guys are building. Obviously, now you're testing it now, and this rocket engine design is, as you said, it's sort of a diesel truck. Once you're up in space, you have this argon, which is a noble gas. It's pretty stable, and then you turn it into a plasma by running it through a radio frequency, like not too dissimilar from a microwave. You strip it of electrons. It turns into a charged plasma, which you then accelerate through superconducting magnets. What are those superconducting magnets powered by?
Yeah, those the superconductor we have now is a conventional low temperature superconductor, not that different from what you see in a MRI machine in a hospital, except that it is designed to have no fluids. So it is a cryogen free. So typically in a hospital, when you get into an MRI machine, you're getting inside the bore of a big magnet, which is itself sort of swimming inside a thermos bottle full of liquid helium. I mean, I know most people don't realize that, but that's really what it is. And no, they're very safe. No, there's no problem there. But the one that we have doesn't have the liquid helium, because for us it would be very complicated to send liquid helium into space and keep it liquid for a long time. So we've designed a superconducting magnet which does not require liquid helium. It has a very sophisticated thermal insulation, and there's a lot of engineering, but so it works without the helium. But it works at very, very low temperature. The magnet operates at 6 Kelvin. So it's interesting to see this contraption, which is a magnet at 6 Kelvin, so it's like 260, what is it, 66 or 67 degrees below 0 centigrade, next to something which is almost 5 million degrees. This is only a few centimeters across. So so there you have the key of the engineering of the rocket. The superconductor that we will use for flight is a high temperature superconductor. It's something more advanced that will operate at 60 Kelvin rather than 6 Kelvin.
High temperature, I love it.
Yeah, we call it high temperature. Maybe not so cold. It's what it is.
Okay.
But I mean, these things already exist, and they are already operating. So we are in the midst of the engineering process of this second superconductor.
Okay. Joseph, is that you?
It is.
Hi, Joe. Welcome. This is Joe Cassady from Aeroject Rocketdyne. He's the executive director of space at that very same company. Let me guess. You were busy looking after the NASA InSight mission, weren't you?
Yeah, it did have something to do with NASA, yeah.
I did have something to do with NASA. Well, we are, I've already introduced you, but I'm glad you're here now. We are talking with Franklin Chang-Diaz from Astra about his new rocket, electric rocket, and we're going to be talking with Dan here in just a minute. But I wanted to point out that you guys are big in the Aeroject Rocketdyne. You guys are working on chemical rockets primarily, correct?
I think he's
actually we're working with Dan too on the electric propulsion.
Oh, good, very good. All right, great
for Mars missions.
Okay, well, is this this seems to be the next big thing? I mean, all of you guys are working on electric propulsion. It seems to me like this is a very promising technology going forward. Dan, as a member of NASA Glenn Research Center, why are you guys interested in these rockets, and what sorts of rockets are you working on?
Yeah, so we are developing lower power variants to what Franklin Chang-Diaz just described. We are looking at 10 kilowatt class electric propulsion devices. There's actually a range of different electric thrusters and systems that are being developed. NASA Glenn has been developing electric propulsion for a number of decades, and the primary focus up until recently has been for NASA science missions. So missions like the Dawn mission, the Deep Space One technology demonstrator, which demonstrated gridded ion thruster technology on a NASA mission for the first time as primary propulsion. And the Dawn mission, which of course was able to visit 2 different asteroids for really a reduced cost of that mission compared to an all-chemical version, which may have not even been possible. And so the range of electric propulsion devices that we are developing range from 7 kilowatt class ion thrusters. The next NASA's evolutionary xenon thruster is been under developed for a number of years. Now is being developed to flight readiness by our partners at Aerojet. And we're also, and that primarily is for NASA science missions, New Frontiers, Discovery class missions. It has a very high efficiency, a very broad throttling range, and so it can complete.
Oh, you just cut out.
Oh. Yep. Cannot hear you, Dan.
Oh, you just cut out. Okay, so there's different class. Are you there, Dan? Can you hear us? We can't hear you.
I can hear you. I don't know if you.
Yeah, I think his audio just cut out.
Yeah.
So Franklin, your rockets are on order of 200 kilowatts. His is on the order of 10 to 13 kilowatts. Is it simply because you're looking at yours are higher power, I guess, because you're looking at doing bigger cargo missions?
There's a matter of scaling. These technologies have their niche. Each one of them has a sort of a niche of optimal application, and the ion engine and the small electric thrusters that they're talking about tend to be optimal for small applications, small spacecraft, as opposed to a very massive rocket such as Bessemer, which is like taking a diesel engine and trying to put a diesel engine on a motorcycle. Let's put it that way.
I'm sure it's been done somewhere, probably here in Florida.
It doesn't quite work. You don't see diesel lawnmowers. You don't see diesel scooters. You see gasoline because the engine scales better. And by the same token, you don't see much gasoline applications in very large trucks or very large earth movers because of the scaling, because of the way the technology scales.
Okay.
I know this is a very, very loose analogy, but it kind of brings a little bit of flavor to it.
Okay, go ahead, Joe.
Mm-hmm.
Yeah,
I was just going to amplify one of Franklin's points. I think, one of the ways we look at it is we're starting small and we're developing, as Dan was saying when his audio cut out, we're developing the technology that can do missions that we could never do before, like Dawn, where we went to 2 different asteroids. But the overall system concept can scale up to these Mars missions, and we can move 50 metric ton class cargo payloads from Earth to Mars very effectively in the near term, just by scaling up what we're already doing today on the science missions and on a lot of geo comsats. You may not realize it, but a lot of geobirds are now using electric propulsion to raise their orbits from where they're dropped off by the launch vehicles all the way to geo and their final destination.
I did not know that.
And it's really, it's actually being done more and more. In fact, the recent Ariane launch actually dropped the satellites off in a bad orbit. It was off by about 20 degrees inclination. And both satellites are using electric propulsion to achieve the desired orbit in geo. And neither satellite will really have a significant loss of life because both are using electric propulsion.
What kilowatt range are they using in those? What kind of
technology? Both of those are in about the 5 kilowatt range.
Oh, wow.
So intermediate to where Dan was talking about with the 7 and 13 kilowatt thrusters.
Dan,
that's what's flying commercially today.
Yep. Sorry about that.
That's all right. What was
on cue?
What was the power of the Dawn rocket? What size rocket?
Those are 2.5 kilowatt thrusters, and on most electric propulsion NASA applications and the geo communication satellites, there are multiple thrusters that make up the electric propulsion system. So most geo comsats utilize 4 thrusters. The thrusters themselves are 5 kilowatt class, and they're operated in pairs typically. For the Dawn mission, it flew 3 thrusters, and I believe 2 were operated at any given time. So you had 2.5 kilowatt thrusters. And what we're doing for NASA's exploration needs is, I think, as Joe mentioned, is developing a 13 kilowatt Hall thruster. That is the individual thruster power. And the conceptual design of the entire system for the spacecraft would be 4 of those thrusters to give you a power capability at a system level of 40 kilowatts. So the vehicle power level would then need to be 50 kilowatts or greater. And so going back to Franklin's point, you see these electric propulsion systems that are building blocks, and you can assemble multiples of them to meet different mission and different vehicle power level needs. At some point, you have just so many of them that going into the next step in terms of system power level, thruster power level, makes sense. And so that's where we think that the 13 kilowatt Hall thruster can be applicable up to about 100 kilowatts or so of vehicle power level. But if you're talking hundreds of kilowatts, you're probably talking about a different system that needs to be developed. And there's a number of people working on those, such as Franklin's Vasimir system.
Right, because he's already at 200, according to the Vasimir design. So, okay.
That's correct.
All right, well, let me just take a break here and remind everybody you are watching a Future in Space Hangout that is sponsored by the American Astronautical Society, astronautical.org. Please go check them out. Thank them for providing these hangouts to you guys, because it wouldn't happen without you. And today we're talking about electric propulsion, and in a minute I'm going to start getting us specific to getting us to Mars, because we've just been talking about the rocket itself and how it works and things like that. So, but in all of our guests, I have Dr. Franklin Chang-Diaz he's the founder of the Astra Rocket Company, Dan Herman from the NASA's Glenn Research Center, and Joe Cassady from Aeroject Rocketdyne, all talking with us about electric propulsion. Okay, so getting us to Mars. Franklin's already working on getting stuff there, trucks. He's building us trucks. We're going to put stuff in his trucks, and we're going to get them to Mars. We've talked in other hangouts about what's going to go in those trucks, habitats and all kinds of other things, 3D printers, presumably, things like that. Franklin, is your rocket, as it currently is Vasimir able to get us there? I mean, how far away, I guess? Let me ask you that. Are we from using this to get it?
Let me add another ingredient to this whole discussion, and that is because we're talking about electric rockets, we need electricity. We need to get the electricity somewhere, and that has been sort of the Achilles heel of electric propulsion, from the very beginning. There was not too much electricity available in space. And nowadays, most of the electricity that you get in a spacecraft comes from the sun, from solar panels. And clearly you want to get as much as you can, but the solar panels tend to get big and unwieldy, and when you're talking about megawatts, the solar energy is not really a credible option.
Franklin, can I just interject real quickly? Is that electricity for these two components, the RF power and to power the magnets? Is that what you need it for?
It's just for any electric rocket.
Okay.
This is in particular in the case of Vasimir, yes, that's where you would put the electricity on the RF power, but in the ion engine, you would put it into the accelerating voltage power supply. So they all need electricity, and that is the problem. So solar electric is what they call it now. They call it SEP. They call it solar electric propulsion. Eventually, when you're talking about sending humans, then you need to talk about nuclear electric, because first of all, solar panels will not be sufficient to deliver humans. And also, when you go to Mars, the sunlight decreases as the square of the distance very quickly. And of course, some of us believe that when you get to Mars, we're not going to really stop at Mars. We might want to continue to go and visit the moons of Jupiter and the moons of Saturn, and you want to have access to the whole solar system. So nuclear power ultimately is a necessity for human exploration. For now, solar is doing okay. And the solar panels that we're developing are pretty good for delivering cargo, delivering your food, your furniture, and your supplies. And astronauts, why they may have to just get pushed in the cannon and fly on a chemical rocket or something like that, or maybe wait until the nuclear reactor is developed. But solar electric propulsion makes a very good case for Mars, for delivering cargo.
Because the solar energy is still enough
It's still enough.
Yes.
It's still enough to send the supplies. They're talking also about hybrid systems where you give the solar rocket, the solar electric rocket, a big kick, with a chemical booster, and you get it going, and then you turn on your solar electric to keep it accelerating, and then maybe you can do pretty well. So lots of little games that we play like that to limp along and go to Mars. People really are in a hurry to get there.
Well, I have a question for Dan. First of all, Dan, or the electric propulsion system that Dan and his colleagues are working on, has a electrical power via different process in the Vasimir, and which I'd like Dan to describe, and then I'm going to have a sort of a follow-up question, and that is probably for both Franklin, Dan, and Joe, for all three of them. If you've got a huge amount of power that a nuclear reactor would power, is really all therefore you have to do is just simply crank it up, supply more power. Will the technology allow that you guys are working on, again, beginning with Dan, will the technology that you've got be able to handle all the power that a nuclear reactor would be able to supply? Or are you going to need engineering or design breakthroughs if we ever do launch a nuclear reactor in space?
That's a good question. It addresses the scalability of the whole thing.
Yeah, pretty much. So Dan, first of all, describe a little bit the system that you are working on and contrast it with Franklin's, and then what keeps you from just really cranking up the power with the nuclear reactor?
Yeah, so the system that we're developing for the Solar Electric Propulsion Project is intended to fly as part of NASA's vision for a deep space gateway. This is a cislunar space station that would prove out technologies and other elements that are required to go to Mars. And so what we're talking about is a 13 kilowatt Hall thruster. Hall thrusters and ion thrusters to me are pretty similar. They use DC voltages, so you don't have the RF that Vasimir does. You apply a DC voltage between an anode and a cathode, and the cathode emits electrons. You use those electrons to bombard the propellant. In this case, it's xenon, which is a heavy noble gas, and we ionize the gas. So now we've created our ions, usually in some kind of either a chamber or a channel, and then we electrostatically accelerate them. So the easiest way an intuitive way to think about it is a gridded ion thruster uses grids with a bunch of holes, millimeters apart, and apply couple thousand volts or multiple thousands of volts between those grids, and those ions will be accelerated away from their like charge towards the oppositely charged grid. That electrostatic acceleration is what generates thrust in the opposite direction. And a Hall thruster, the grids are removed, and you replace them with a magnetic field that retards the charged particles from going in the direction they would like, and that sets up an electrostatic field. So it generates its own electrostatic fields instead of using grids. The technology, as we mentioned, it's 13 kilowatts for the system, can be combined to generate electric propulsion systems up to 100, 150 kilowatts for a vehicle. And the technology itself is extensible to even higher power thruster variants. For example, NASA Glenn has designed and demonstrated in the laboratory environment a 100 kilowatt class Hall thruster. And so with the technology itself is scalable to increase the vehicle power level and electric power level as well.
What is the engineering or technical limit to the amount of power? This is, again, I want to get back to either Joe or Frank, but Dan, what is the technology or engineering limit to the amount of power, the amount of thrust that you can produce? Do you get material breakdown? Magnetic confinement? What happens?
So we've not yet, I think, hit that limitation with regard to the Hall thruster technology. It's really a limitation in space that is available. It's not as high current density as the Vasimir engine. So as long as you can package it on the vehicle, which could become a challenge as you get to hundreds of kilowatt class vehicles, the technology itself scales, and you can combine multiple thrusters to have a very basically using them as building blocks to meet a number of electric power needs for different spacecraft. So we know the technology, we've demonstrated the technology is scalable up to 100 kilowatts and in excess of that. And so you can actually get hundreds of kilowatts vehicle. So really limitation, I think, is going to be space. Space availability on the spacecraft itself would be probably the first limitation we'd run into.
So Franklin, same question to you. I was in college so many years ago. Electricity and magnetism, I did not do well in electricity and magnetism. Although,
that's a hard course, Harley.
Well, it was so many years ago. I think Michael Faraday was still alive. So in your case, I mean, the issue of magnetic confinement has got to be a major issue as you crank up the power and try to increase the thrust. But from your design, or in your design, what limits?
Yeah. Yeah. Well, you know, the Vasimer scaling can easily go all the way to megawatts. Even the rocket we have here today is capable maybe of 0.5 megawatt. We have never pushed that because the laboratory just cannot allow it. I mean, we don't have that kind of capability in the laboratory to do that, but the rocket would probably be able to take it. The genesis, you know, the genesis of the technology that we have comes from very high power machines. These are, you know, the genesis is from the thermonuclear program, the fusion program. A lot of people back in the 60s and 70s began to fool around with plasmas of very high density to, in essence, replicate a small sun on Earth, create a small sun on Earth. And that, you know, proved to be a lot more difficult than we expected back in those days. But the technology developed for confining very dense plasmas with magnetic fields. The challenge for us is to miniaturize everything, to make it all lightweight, to make it very compact. But the physics is very very favorable in terms of what it can do. It's the engineering what is the biggest challenge.
Yeah.
So I wanted to show this. I don't know if this is the right thing to show right now, Franklin, but you had talked about this. Is this addressing what Harley was talking about with more power and the scalability of this technology? You have here a chart that shows you know, how fast you could go to Mars versus the power of the rocket.
Yeah, yeah. Well, this really relates more to the technology of the power source.
Okay.
The nuclear reactor in this case, or the solar power source. But you know, we are more focused on nuclear power to deliver those kinds of. You can see the horizontal axis is written in megawatts.
Right.
You know, so we are really not talking too much about solar power here. So I tend to
10
always,
megawatts is the low end.
Reminisce. I always reminisce on this topic on what happened in the 1950s. I guess it was 1958 when the USS Nautilus, you know, the first nuclear submarine, dove in the North Pacific and reappeared a few, maybe about a week or so later, in the North Atlantic. And how did it do that? I mean, it did that by going under the North Pole, which was covered by ice.
At the time.
Covered with ice. And this was a feat. This was a feat that could never be done back in those days with a conventional diesel power submarine. It was nuclear power would enable this paradigm shift. And this is, to me, the paradigm shift that needs to occur for humans to really be able to explore space in a robust way. And so what this chart shows is different technologies. You see on the right, there's a listing of the various technologies, the maturity of different technologies in terms of the number of kilograms per kilowatt. So this, how heavy is this nuclear reactor? You know, if you are talking about 1980s technology, typically nuclear reactors would be about 20 kilograms per kilowatt. And if you see that on the left, the minimum of that is at about 140 days. That's about as fast as you can go.
Right. The y-axis is the Earth-Mars transit time in days.
That is correct, and it will take you about 10 megawatts to make that mission. That's about the best you could have done in 1980 with that kind of technology. If we go to you know, sort of near technology, 2010 nuclear technology, you can go better. You can do better. About 110 days transits with about 15 megawatts of nuclear power. And then if you push the technology down to, you know, 4 kilograms per kilowatt or 2 kilograms per kilowatt, now you start seeing some really interesting missions. And then further, you know, if you go to the extreme, which I don't claim that we can do that right now. Certainly,
a half a kilogram per kilowatt at around 60 megawatts minimum.
Yeah, that is, of course, it is almost like the holy grail, you know. But you can see that the physics allows you to make very fast missions, and that's the promise. You know, back in the early 1800s, when aircraft were beginning to be considered, why we wouldn't imagine the flying jumbo jets today with you know, nearly 1,000 passengers. I mean, somebody would ask someone back in the 1800s if we could fly a jet. Well, they probably didn't even know what a jet was, but fly an aircraft with 1,000 passengers, they would have told them, "You're crazy." You see? And
right.
So this is what I'm trying to say. I'm trying to push us to think out of the box and think big.
Right. So I think to Harley's question, if we can get these reactors down to a half a kilogram per kilowatt and get them up to 130 megawatts of power, then your engine or an engine like it can get us to Mars in 40 days.
Nuclear power is by definition a very high density, very high density power source. I mean, nuclear reactors on Earth today put out gigawatts. You know, there's like 2 or 3 gigawatts. So 140, 150 megawatts is nothing. 1747 on takeoff is 200 megawatts. You know, just to give you a scale. So it's nothing to get so wrapped up or, you know, riled up about.
That's right. Just get a 747
You have to think. You have to be, you know, dream big. You know, you can't just.
Well, this is very promising technology, I have to say. This is pretty cool. And we're already using it. It sounds like it's tested, too. Go ahead, Joe. Did you want to say something?
You're
getting a phone call.
Ringing. Oh, tell them you don't need a car warranty, Harley. I was going to bring up, Tony, the one thing in Franklin's chart, too, when you said the reactor needs to get down to that specific mass, it's the overall system. And so the other part that we have to deal with in space is the heat rejection. And that has always been a little bit of a problem in terms of getting it.
Because these superconductors need to be cold?
Well, you have to get rid of the heat of the reactor. Remember, the best cycles, a Brayton cycle is going to be about in the mid 30s. And so something like 70% of the heat, 60 to 70% of the heat that the reactor is producing has to be essentially dissipated into space. And so what you see in the concepts when you look at something like a space reactor design is usually some big wings that aren't solar panels. They're big arrays of radiators that are there to dissipate that heat.
Okay.
And so that's the other part of the challenge is the reactor itself is very compact and power dense, as Franklin said, but we also have to deal with the rest of the system. And then, of course, there's a loop of usually liquid metal and things like that that are used to pump that heat out into those big arrays of radiators. I'm a fan. I really believe we need to go that way, like Franklin said. I think we're coming at it from the perspective of scaling up from what we are working with today at modest power levels to probably something between 300 and 500 kilowatts as a upper limit for solar. And then, once you get up to about megawatt class, where Franklin's thinking, that's when you have to cut over to nuclear.
Okay, yeah, that makes sense with the
transition.
transition.
That's the right way to look at it. And we in our company, we're very sensitive to our investors, and they don't, going to Mars now is not a very good business, And so we have to explain to them that the Vasimer, the first embodiments of the Vasimer, is really solar electric.
Right.
We are developing the technology for solar electric.
And as you point out, that's still good in the Mars regime. So that we're still on track for that. I have a lot of questions, guys, and so I want to get to some of them. Joe, I'm really sorry, but I think you've got a lot of background noise where you are.
Oh yeah, sorry about that.
Guy's kind of angry. It sounds like you're in the middle of a kitchen.
Yeah.
If you wouldn't mind, just maybe muting your microphone.
Shop.
Yeah, that's okay. Just maybe mute it, and that would be. You're the first one to do this from a Starbucks. Okay, so Cosmic Lettuce was asking a long time ago, back when we were talking about your engine, Franklin, and I had the schematic up about the RF antennas, but they weren't antennas. You were calling them couplers. What frequencies do those operate at?
Yeah. Well, the first antenna, the one that makes the plasma, operates in the FM band. So it's 6 megahertz. So it's very, very.
It's like a real powerful FM radio, huh?
Like a real FM radio, except these radios are extremely compact. Very, very lightweight and very high efficiency. So these are not like the radios that you would, go and buy. And then the other system, the second antenna or the second coupler, operates in the AM band. So even longer wavelength at 500 kilohertz. So these are very, very simple waves and very conventional in their structure. They're huge. They're very long wavelengths, but they work very well in tiny enclosures because the plasma is reactive to that. It's like a